Just a fair warning here, this isn't a concrete example of reduction of order. It's actually a kind of intuitive explanation of why it works. So we're going to be working with this generic differential equation, p of x, q of x, for the coefficient terms. And we're just given that y1 is a homogeneous solution. We don't actually know what it is. And we're going to go from there. All right, so normally we guess y2, the second homogeneous solution, is our unknown function v times y1. And then next things we do is we take a couple derivatives, plug in y2 to the ODE. So y2 prime is going to equal v prime y1 plus v y1 prime. Then y2 double prime is v double prime y1 plus v prime y1 prime. So that's the product rule from the first term. Then we have the product rule for the second term. That's v prime y1 prime plus v y1 double prime. And I can simplify that a little bit. That ends up being v double prime times y1 plus 2 v prime y1 prime plus v y1 double prime. All right, next step is we plug in y2 to the ODE. So y2 double prime plus p of x times y2 prime plus q of x times y2 is equal to 0 in order for y2 to be a homogeneous solution. So then we get to plug in all the things for y2 here. So y2 double prime was v double prime y1 plus 2 v prime y1 prime plus v y1 double prime. So that was the y2 double prime. And I have my plus p of x times y2 prime, which is v prime y1 plus v y1 prime. Then I have my plus q of x times y2, which is just v times y1. And that all has to equal 0. All right, next thing to do is we're going to group our terms. So I want all the v double prime terms. There's only one, and I'm going to rearrange the y's in this case. So we have y1 v double prime plus, then I want all of my v prime terms. So I've got a v prime term here. There's 2 times v prime times y1 prime. So I have 2 y1 prime. And then I also have a p of x times v prime times y1. So plus p of x times y1. Then I've got all my v terms, which I think will fit in there. All right, that's to equal 0. So let's see, I've got a v times y1 double prime. So y1 double prime. I've got a p of x times v times y1 prime. So plus p of x times y1 prime. Then I've got a plus q of x times v times y1. So plus q of x y1. Okay, that got a little scrunch there, but let's take a look. We have our y1 v double prime. We have our 2 y1 prime plus p of x y1 times v prime. We have our y1 double prime plus p of x times y1 prime plus q of x times y1 times v. So this term is supposed to disappear, and actually the reason it disappears is because this is essentially a copy of the left-hand side of the ODE when we plug in the homogeneous solution y1. Right, so going back, y1 of x is a homogeneous solution. What that means is that if we plug y1 into the differential equation, meaning y1 double prime plus p of x times y1 prime plus q of x times y1, it will equal 0. That's its definition. If y1 is a homogeneous solution, y1 solves the original differential equation. That means that y1 double prime plus p of x times y1 prime plus q of x times y1 has to equal 0. So what that ends up meaning is this equation we wrote down here, y1 times v double prime plus 2 y1 prime plus p of x times y1 all times v prime plus this piece right here is the differential equation. So we actually just end up with 0 v equals 0. And then from there, right, if I just get rid of the 0v, I have y1 double prime times, I have y1 times v double prime plus 2y1 prime plus p of x times y1 times v prime equals 0. And then the reduction to order trick we usually use to make it a little more intuitive, less confusing to solve the problem is we'll say w of x equals v prime of x, then w prime of x equals v double prime of x. And so we get a first order differential equation to solve, essentially y1 times w prime plus plus parentheses, 2y1 prime plus p of x y1 w equals 0. And then from there, we can try to solve for w. Once we solve for w, we can go back, solve for v. Once we solve for v, we can go back and we can solve for the second homogeneous solution, y2. All right, so the key here is that this thing shows up essentially a copy of the original differential equation. The reason that actually happens is kind of there's this half of the product rule where you kind of don't do the derivative of v. So right, there's this piece, and there's this piece, right? I took the derivative of y1 prime, not the v. And then there was these pieces, the same one. That was a terrible arrow. All right, close enough. So this one was like v, y1 double prime, v, y1 double prime. This is kind of the part of the product rule where we didn't take the derivative of the v part. We only did the y1 part. And so by doing that, you end up with v times y1, we have v times y1 prime, v times y1 double prime. You put that into the difference equation, you get v times y1 double prime, we get p of x times v times y1 prime, we get q of x times v times y1. You end up getting this little copy of the original ODE with all the y1 terms with their derivatives and this part of the product rule where we never took the derivative of v. So that's the reason it works. And then it can be a little tedious to actually solve for w and then to solve for v and then to plug that in and get y2 again. But that's the idea, and it's all possible because the differential equation here is linear. If the differential equation wasn't linear, you wouldn't get this nice separating of this y1, all the derivatives, times just v term. It would be a lot worse. So that's right, this method only works for linear second order differential equations.